in the last class, we introduced the concept of short channel effects. Acronym is SCE. Okay, and the first thing that we spoke about was channel length modulation. CLM. And what was this? If I have to summarize this effect, the delta L by L is going to be modeled as lambda times VDS. Okay, so therefore the equation, the drain current equation gets modified as, in saturation, mu n C ox W by L, right, into VGS minus VT whole squared into 1 plus lambda VDS. Right, this is what we said, and primarily it's in saturation that you will see these effects, right, because VDS has to be large. Okay. So moving on with the short channel effects, in this class we will discuss what is known as velocity saturation. So as we discussed last class, you have a source and a drain in a long channel device. They were placed very far apart. Oxide here, N plus P, right. So if you applied a drain potential Vd here, of course with the source and the body both grounded, and you applied a Vg, right, then what would happen is the source, right, this is the source, drain. The source will give you some electrons and will get accelerated, or it will drift with some velocity through the channel, right, and then get to the drain end, and that's how current was generated, and we derived the equation for the current, right. The source basically sources the charge carrier, the drain collects them, that's why the name source and drain. Okay. So in an NMOS transistor, the current, because it is because of electrons, current flows from drain to source, opposite of the flow of charges, right. So the IDS is basically like this. Okay, and these electrons would get accelerated or would attain a larger drift velocity, not accelerated in this lattice actually, it attains a larger drift velocity if you apply a larger voltage on the drain end. Okay. So basically that's simply related to the electric field E, and the max is VDS by L. If you just consider the two ends, then the electric field is VDS by L. Okay. Now what happens is, when you start bringing this drain very close and shrinking this transistor, right, and making it look like this, of course now we have the problem of these depletion regions eating into the channel and all that. Okay. Apart from that, what we had to do was, when we brought this drain very close to the source, I cannot continue to apply the same drain voltage, max drain voltage that I would have applied for a long channel device. Why? Because the device will break down. There is a breakdown electric field beyond which that all those properties don't hold, right, of a semiconductor and all that. So therefore we had to lower the supply voltage also as we scaled these transistors and made them much smaller, right. So therefore my VDD also started dropping with technology. Okay. Now, in spite of dropping the VDD, it turns out that there is only a maximum drift velocity that these electrons can attain in this lattice. Okay. So, there is a drift velocity Vd is about 10 power 5, I think, centimeter per second, if I am not mistaken. Okay, let me check that number. So that, yeah, it's about 10 meter per second. Okay, the velocity cannot go higher than this. Why is this? Of course, because there are atoms, there are, you know, a lot of things to collide with and all that stuff. So it cannot accelerate beyond this. Okay, that we have to just take this fact as a thing. Now we have to incorporate this into our model. Okay, but look at our current equation. Where is the drift velocity in this? We don't have a drift velocity term in any of these equations. So this is through mobility and all that stuff, right? So somehow we have to now bring in this effect of maximum drift velocity into our current voltage equation. So we have to translate this maximum drift velocity to a maximum voltage that is permissible, right? So let us look at that. Drift velocity is mu times E. Okay, so if there was no, if the channel was long enough, right, then what, how would this equation look like? Vd versus E, it would basically be a straight line, right? Now what are we saying? This saturates, right? So this is somewhere 10 power 5 meter per second. Okay, so that means there is a critical electric field beyond which this saturation takes place. Okay, and therefore I will write this Vd sat, let me call this as Vd sat, the drift velocity saturation value, okay, is going to be mu n, of course, into Vd sat by L. Okay, therefore Vd sat is equal to Vd sat velocity, drift velocity saturation value into L divided by mu n. So now what have we done? We have taken the drift velocity problem and translated to a voltage equivalent value, right, which means to say that if I apply a drain voltage that exceeds this Vd sat value, then I cannot get any further acceleration or any further increase in current, right? Again, not acceleration, sorry, it is any further drift velocity, which means that my current will saturate. Okay, so now how do I incorporate this into the equation? So we have applied a certain VGS, okay, then we start increasing the VDS. Okay, what will happen? Sorry, so let's consider two cases. Okay, VDS is small, okay, and then VDS is large. No, I am considering VGS, sorry, large. I am going to sweep VDS. Okay, so I am going to increase my VDS here and look at IDS. So for the small value of VGS, what will happen initially? It will be in, of course, no, assume that VGS is slightly above threshold voltage, that's what I mean. Okay, small but greater than VT. Okay, good point. So when I now sweep my VDS, what region will it start operating in? Yeah, triode region or linear region. So it will go like this, right? Now where is your VD sat, right? Let's look at this. Let's say my VD sat is here. This is the critical VD sat voltage. Beyond this, if you cross, then you will saturate, correct? So therefore, if VGS is small enough, then it can achieve the saturation current much earlier. Remember that because at the drain end, my VGS minus VT minus V should be greater than 0. So if VGS is small enough and the original saturation happens, then the current will just saturate here. Right? Now again, if I take the next VGS again, which is quite small, then this will go like this. Further if I go, it will go like this, and this behavior can be quadratic because we are still in the old saturation region only, correct? Now if I apply a very large VGS, then what will happen is this point at which it saturates is going to be where this will be. This is for a large VGS. This is VGS minus VT, and assume this is large. Then the current will actually go up like this, okay, and then saturate here. Normally it should have gone on in the linear region until here and then saturated here. This effect of lowering the current is due to velocity saturation. Okay. So the point I am trying to make is, it does not mean that a transistor cannot go into the regular saturation region if velocity saturation exists in the technology. It can, it depends on the VGS value, because if that saturates first, right, then it cannot go, it cannot even enter this velocity saturation region, right. Basically, if the drift velocity is small enough, then the transistor behaves in the old fashion that we were talking about, okay. So now the question is, for a long channel device, did this velocity saturation effect not exist at all? Yeah, exactly. It's not that it doesn't exist. Of course it exists there also. It's just that the VDS I have to apply is so large that it is out of the range in which we are going to operate the device in, and therefore we don't worry about it there. That's all. There also, if you increase the VDS beyond a point, you will hit this 10 power 5 meter per second and then it will saturate. But that's not even in the interesting region of operation. You are well above VDD there, and therefore we don't worry about it in a long channel device. Okay. Any questions here? Okay, so how does this current look like now? That is just the intuitive picture that I gave you, right? So how do we incorporate this into our equation? So the drain current is going to be the following. Okay, of course it is 0 if VGS is less than VT. Now if it is in linear region, right, mu n C ox W by L into VDS into VGS minus VT minus VDS by 2. Okay, I am not incorporating the channel length modulation. We can add that effect later. Okay, if VDS is less than or equal to VGS minus VT. And earlier, if it had to go into saturation region, it would be WL half of VGS minus VT the whole squared if VDS was greater than VGS minus VT. Now somewhere in between these two regions where you are going from linear to saturation, if this saturation drain voltage VD sat occurs before, as I am sweeping my drain voltage VDS, then the current will saturate to that value, and that value is just given by, in the linear equation, look at this, in the linear equation you substitute VD sat and that is the value of your current. It cannot go beyond that. So this will become mu n C aux W by L VD sat into VGS minus VT minus VD sat squared by 2. Oh sorry, VD sat by 2. Yeah, I brought that out. Okay. So now what is the condition under which this holds? The condition is VD sat is less than VGS minus VT. If that happens, okay. So now what I will do is, we have too many regions of operation, linear region, saturation region, velocity saturation region, and by the way, let me just put it down. This is linear, right, or triode, or resistive region, right. It behaves like a voltage control resistor in that region. This is a saturation region, okay, and this region is called velocity saturation. So now I have 3 different regions of operation, and this can be quite confusing, and therefore we have what is known as a unified current model. Again, this is an abstraction that works very well for this course, okay, and this is more than sufficient for us because the regions of operation are going to be sort of in the extremes. VGS will be 0 or VDD, this kind of thing. Okay, we are not too worried about the details in between. Therefore, I will write my current. Okay, just look at these equations here. This equation, let me put that in blue, is basically this equation with VDS equals, and this equation is what? VDS is equal to VD sat. So what is really happening? It is the min of 3 different values that is appearing in that term there, right? The VDS term is getting replaced by either VDS or VGS minus VT or VD sat, whichever is the lowest, because you look at various regions. Here VDS is less than VGS minus VT first, so then it becomes a linear region. Here VDS has exceeded VGS minus VT, therefore VGS minus VT comes in. Now the second one is VD sat appears even before VGS minus VT, therefore it saturates even earlier. Therefore the natural way to write this is mu n C aux W by L into V min, okay, into VGS minus VT minus V min by 2, okay. And now I will incorporate even this channel length modulation straight away, okay, into 1 plus lambda VDS. Of course, this may, if you ask me whether this happens even in the linear region for small values of VDS, it may not. But the point is, because this is a model that we are building, we need to have continuity across regions. Otherwise, the simulator will not be able to simulate all this correctly. Therefore, you put this in where the impact is not very large, because if VDS is very small, lambda is already a very small parameter. 1 plus lambda VDS will approximately be 1. So it will not affect your equation there, but it will help attain continuity across regions. And that's why you just put it in for all regions of operation. Now what is V min? Is minimum of VGS minus VT, correct, comma VDS, comma VD sat. So given a problem, if you have to identify which region of operation it is in, you calculate V min, which is a min of these three. If this turns out to be the answer, it means the transistor is in saturation region. If this turns out to be the answer, then it is in linear region. And if this turns out to be the answer, it is in velocity saturation region. Okay, so this really simplifies our analysis and mathematically abstracts the whole thing out very well and quite consistently also. Okay, it deviates a little bit from reality, because what we are saying is the point at which this velocity saturation happens is like a straight line. There is one VD sat, but that can sort of change a little bit apparently. Okay, if you go to a device physics course, you will see that that's not fully true, but for the purposes of this course, it is more than sufficient. Okay, so now I'll rewrite this, yeah, VDS, because that delta L by L, right, see where is this lambda VDS coming from? This is basically modeling the delta L by L term, and that is purely determined by the reverse bias voltage on the drain side, right? That only that modulates this depletion region at the drain end, and therefore that can be only 1 plus lambda VDS. It has nothing to do with VGS or VD sat. Okay, yeah. Now again there are sort of too many terms, so I will combine this and write it as Kn prime. Okay, then I have this V min, VGS, whatever. Okay, and I have my threshold voltage equation. What is it? It is VTH naught plus gamma times root of mod VSB plus psi s minus root of mod psi s. So if you look at this current equation, I have 5 parameters. Okay, I have 5 parameters, not just the current and threshold voltage equation. One is Kn prime, second is my VD sat, third is lambda, fourth is my VTH naught, and the fifth parameter is gamma. Okay, these 5 parameters characterize uniquely a particular transistor in that technology. So what do? You don't worry about solving device physics here. You go and fit these parameters through measurements in a particular technology. You fit these parameters and you specify this in a particular model file. Yesterday, if you remember, in the tutorial, you were shown a model file which had like 54 parameters or something. This is a much simpler model than that. That is, it incorporates many more effects and is far more sophisticated, which is understandable because reality it is far more sophisticated. But this is effectively what is known as the level one spice model. Just 5 parameters, and if I define the current in this particular way and the threshold voltage in this particular way, right, then I can obtain the current if the fab gives me these 5 parameters. Of course, it's a very simplified equation. Now my question is the following. I combined mu n into Cox, right, and what is Cox, by the way, just to remind you, it is epsilon oxide, right, by Tox, oxide thickness. Now why didn't I combine W by L into this equation? Why didn't I say Kn prime into V min, right, into Vgs minus Vt? That is the current equation. Why did I separate this mu and Cox alone as one parameter and kept W by L outside? Yeah, you can change, or I want to differentiate between two things. One is a technology parameter, other is a design parameter. So these level 1 spice model, these are known as technology parameters. Which means that once I have shrunk my technology to a new node and I have defined the feature sizes and all that stuff, these values or these parameters are not dependent on the design parameters. So as a designer, what is the freedom that you have to tweak? You can tweak W, you can tweak L in analog designs. Okay, in digital design, of course, for high speed you have to keep it as close as possible, so it's effectively fixed, right? But you can tweak W, you can tweak L, and you can tweak the voltages. So therefore these parameters should not be combined with the technology parameters and sort of confuse you. You should know exactly, when I say it's a technology parameter, it means it's fixed. You cannot propose a solution that says I will change the technology parameter. You have to propose a solution where you change the design parameters and achieve the goal that you want going forward. So that's why in this course we will always separate the terms out as technology parameter and design parameters and bring out the dependence very clearly on the design parameters. Okay, for the oxide thickness, for example, that is fixed for all transistors. Once you scale to a new technology, in 14 nanometer it's about 1 nanometer. 14 nanometer technology, the oxide thickness is about 1 nanometer for all transistors, including PMOS transistors, right? You have another variety called a thick oxide device where the oxide thickness is slightly larger, but that's a separate model. But even there, across NMOS and PMOS, the oxide thickness is fixed. Okay. Again, VD SAT, if you scale to a new technology, then you get a new maximum drain voltage that you can apply, before which the velocity will saturate in the channel, right? So that again is given to you as a parameter. Now the question is, for what value of channel length are they giving you this? Because I just told you that L can be varied, correct? In analog designs, I can change L to even 10 micron, right? In a 14 nanometer technology, it's possible. So does this VD SAT apply there? So the answer is no, it does not. When they say they give you a model file with these technology parameters, there is a region of operation where this is valid. If you try to take this model file and apply it for some random region of operation, the fab will not give you any guarantee that it is even expected to work. These parameters have been fit very specifically to measurements made on devices in a range of L length, width and supply voltage conditions. So the model file, they will tell you, right? In the model file yesterday you saw VDD equal to 0.8 volt. What if I apply VDD equal to 1.6 volt in that? The answers can be totally wrong, right? So these model files are actually specific to the application that you are doing. Here in digital design, we are fixing our L because we want maximum speed. Therefore, this VD SAT makes a lot of sense there. Okay. So what about the the lambdas? All of these parameters have some sort of a length dependence, because if I take the length very far away, then this doesn't really affect it at all. Of course, sometimes they will fit these things so that there is a dependence on the L also. Okay, you can fit it to that kind of an equation as well, right? Now threshold voltage VTH naught. Okay, this again has no dependence on L and W, as you can see in this previous equation or the equations that we derived earlier. It's independent of L and W to a first order, and you get one particular number that the fab says this transistor has a VTH naught of 250 millivolt, right? It is independent of L and W. Okay, but again it doesn't mean that I can take L to 10 nanometer and expect it to give me the right threshold voltage. No, it is for that region of L and W where that is valid. Okay, similarly the gamma is fit to a particular value, and these 5 technology parameters put together constitute what is known as the level 1 SPICE model. Okay,